One last area that we might be interested in these different ideal gas processes would be in figuring out how much work we can make a gas do on its surroundings and using these PV diagrams to help us understand that. So far we've been thinking about this in terms of how much work do I have to do to the gas to make it undergo each of these changes. But in addition to doing work on the gas, we could use the gas itself to do work on something else. So for this, think engines. So in an engine, we squirt a little fuel into the piston, the fuel gets ignited, that increase in temperature, that rapid heating process, it causes expansion of the gas, which pushes the piston outward, and that pushing force drives the car forward, indirectly, of course. But so in this situation, we're going to be looking at work done by the gas, and we're going to think about that as being positive work at this point. So before we were looking at work done on the gas, called that positive. Now we're going to think about work done by the gas. So work is positive if the gas is applying work to the system around it. So that's if we have expansion. So if our volume is increasing, or if delta V is greater than 0, if delta V is positive. So we've actually done a little bit with calculating work for certain processes like this. We said if we have a constant pressure or an isobaric process, then the work is equal to the pressure times the change in volume. Okay, so work here would be equal to the pressure, which is 100,000 newtons per square meter, or pascals, times the change in volume. We start out at 0.003 cubic meters. We end at 0.013, so we have 0.01 cubic meters is our change, getting larger, so it's a positive value. So work then would be equal to 1,000 newtons per square meter times cubic meters would be Newton meters, or joules is the unit we use for work. Now you might notice that the 100,000, that's this distance right here is 100,000 newtons per square meter, or this distance right here is 100,000 newtons per square meter, and then this 0.01 cubic meters, well, that's this distance right here, or this distance right here. When we multiply those together, we are finding the area of this rectangle. And this isn't a fluke. It turns out that in general on these ones, if we find the area underneath the curve on a PV diagram, that's equal to the work. So the work is equal to the area under the curve. Or if you've done calculus before, we can write this as work is equal to the integral of P with respect to V, the differential volume there. And then the limits of this integral are set by how much we're expanding or contracting here. Okay, so if we move down here to a case that isn't constant pressure, we can still calculate the work done by this gas, or the work done on this gas, whatever the case may be here, by doing the area underneath the curve. So I have my curve makes some shape like this. So that's a trapezoid. If you know the equation for the area of a trapezoid, then we can use that. If you don't remember that one, that's fine. We can break this up into a triangle and a rectangle. And one thing that's worth noting here is that in this case we start out, the little arrow tells us that we start at a volume of 0.013 cubic meters and end at a volume of 0.004 cubic meters. So in this case, the system around the gas is actually doing work on the gas. So here, the work done by the gas, performed by the gas, is going to be a negative value because we have contraction in this case. So we can already say work is going to be a negative something or other. Okay, so to get the area, we'll just do the area of this triangle, so that's 1/2 times the base, it looks like is 0.009 cubic meters, times the height, which is 70,000 pascals or newtons per square meter. Okay, so if we do that calculation, 0.009 times 70,000 over 2 is 35,000. We get 315 joules for that section. And then here, the area of that is going to be 0.009 cubic meters. The length times the width or the height here is 30,000 newtons per square meter. So 0.009 times the 30,000, that gives us 270. Okay, so our work overall is going to be 315 joules plus 270 joules, so 585 joules, but negative 585 joules. Negative because we have contraction, so the gas is doing negative work on its surroundings, or the surroundings are doing positive work on the gas. Okay, now typically in something like an engine or any other application for doing work on the system using a gas, we're going to be concerned not just with a single change in pressure and in volume here. We might do multiple cycles, something that repeats again and again and again, like the strokes of an engine repeating again and again and again. So we look at cyclical processes. Now, if we made this one a cyclical process, we went to the right and then back to the left and then back to the right and then back to the left. Every time we went to the right, we'd do a positive 1,000 joules of work on the surroundings. Every time we went to the left, it'd be a negative 1,000 joules on the surrounding. So for one complete cycle, we'd have a total work of 0. And the same is true here. If we went up and to the left like this, and then back down and to the right, and back and forth, and back and forth, in one complete cycle, we'd end up doing 0 joules of work on our surroundings. So to have some net work that we're doing on the surroundings, we need to not travel back on the same path that we travel forward on. So we need something like this. So, just briefly here, it's we're thinking about this, that for this section, we are expanding and at a constant pressure, so this would be isobaric expansion. For this section, our pressure is dropping, but the volume is staying the same. Volume the same is isochoric. And then pressure would drop if our temperature was dropping. So this would be isochoric cooling. And then here this would be constant pressure, so isobaric. And instead of expansion, we have compression. And then this must be isochoric. If pressure is going up, temperature must be going up, so this would be isochoric heating. Alright, so 4 processes that are strung together in a row, and we can see that let's just see what our total amount of work is for this process. So let me just clear a little space here. So we'll go around one time here, and it doesn't matter where we start on this. Anywhere we start will give us the same value. And I'm just going to color code this. So anytime we have positive work, I'm going to show that, I'm actually going to use green for positive work. So let's do negative work in red, and green, we'll do positive work. I don't know, green just feels more positive to me. I get to go on the green light and you have to stop on the red light. I always feel so negative about having to stop at the red light. Okay, I don't know what my rationale is there, but green needs to be positive. I know that much. Okay, so let's start right here. And then we'll go around this cycle one complete time and figure out how much work the gas does, or how much work is done on the gas for one complete cycle. So we do the area underneath the curve for this section first. So that'd be this whole area underneath the curve. Okay, so the work for that, our work is going to, I better be consistent with my work total here. Be consistent and make sure that these are positive and negative correctly. So for expansion, we have positive work, and then the value for that is just going to be the area inside this inside this rectangle, which is 100,000 pascals, or newtons per square meter, times, let's see, the length of this, or the width of this rectangle looks like 0.008, and that's cubic meters. Okay, and then plus, okay, and let's see, for this section, our volume isn't changing at all. If we tried to do the area underneath this, we'd get, well, it's a rectangle with a width of 0, so there's no area there. When we come back this direction, that's a compression, so that's work being done on the gas. We'll make that red. So that'll be this section right here. Okay, so that section has a value, so that'll be a negative. I'll just make a note to myself, negative. Then we have a 50,000 Newton, or 50,000 pascals, or newtons per square meter. Okay, times the 0.008 cubic meters. Clean this up a little bit. There we go. Okay, so our overall work then, work total, is going to be equal to, well, I see that my green is going to be bigger, so we're going to have a positive amount of work here. 50,000 times 0.008 is going to be our answer. So 50,000 times 0.008, that's 400 joules of work for one complete process. Now, in this section, or in this example, we took this big rectangle and then subtracted this smaller rectangle, leaving us just with this rectangle here. That's the area that was enclosed by our initial curve. You can see the blue lines underneath there. So the area enclosed by a curve in a cycle, in a cyclical process like this, that's going to be the total work in the process. Now, we might have positive work overall or negative work. We have to just look to see, okay, well here our expansion is at a higher pressure, our compression is at a lower pressure. So, the work done here, that positive work, that would be greater than the work done here, the negative work, so we end up with overall positive work. But it's just this area inside the curve that gets us our overall work, or our total work. Now, the curves that we deal with, or the paths that we deal with, they don't have to be quite so simple as this, dealing all with rectangles, they're going to be fairly straightforward because in AP Physics at B, you're not assumed to have taken calculus. So all the lines that we deal with are going to be straight lines. We're not going to have any curves, but that doesn't mean that we can't get a little bit more complex in our calculations. So if we want to know the work done in this process where we have some expansion with increasing pressure, and that straight line, it doesn't really, well, let's see, pressure and volume are directly related there, so that must mean, no, we don't have a relationship for that, or a name for that kind of relationship, or for this one. So it's not one of the special cases we've talked about. That's fine, though. We can still do the calculation. So the area inside this curve, or inside this, this path, is going to be equal to the total amount of work done. And we can see that we're expanding at higher pressures. So here, that's going to be a larger amount of work than our compression section at the bottom. So overall, this is going to be positive work. So work, we can tell right at the beginning, is going to be a positive just because, well, we have the area bounded by the curve in the expansion direction. That's higher up than the compression direction here. So to figure out the area of this, again, I'm just going to break this up into pieces for which I know area equations. So you can kind of break that up however you want to. Try and just keep it as simple as possible. Okay, so we got 4 shapes here that we need to find the area for. Sorry, 5 shapes. We need to find the area for. We'll add all those together, and those are going to be that's going to be the positive work done for this system. So first off, let's do this little triangle so that it'd be positive. So it's 1/2 times the base, and here it looks like that's 0.004. And that's cubic meters, times the height, looks like 30,000 newtons per square meter, okay, plus, let's see, right here, there we go, right here we've got a rectangle that's got a length of 0.004 cubic meters, and a height of 30,000 newtons per square meter. Plus this one, we've got a length, looks like, see, 0.008 to 0.014, so that'd be 0.006 cubic meters, times the height, must be 60,000 pascals, or newtons per square meter. Okay. Plus this one now, we've got a width there of 0.006, 006 rather, cubic meters, times a height of 40,000 newtons per square meter, plus, last one, triangle 1/2, times the base, we'll say, is this one, so that'd be 0.004. Running out of room here. Cubic meters, times the height is 40,000 newtons per square meter. Okay, so we'll punch this all into the calculator to get the total area inside that shape, which is the total work done. So we'll have 0.004 times 1/2 is 0.002 times 30,000 plus 0.004 times 30,000 plus 0.006 times 60,000 plus 0.006 times 40, 3,000, plus 1/2 times 0.004 is 0.002 times 40,000 and we get a total work done of 860 joules. Okay, now I didn't worry anything about the parts of the shape that are down here, the negative work done there, because I would also be doing the positive work in this direction. So the positive and the negative for that section, they just cancel out. So we don't only worry about the area inside these curves then. We just have to make a decision about, is it going to be positive work or negative work based on whether our expansion takes place at a higher pressure or at a lower pressure. If expansion takes place at a higher pressure, then we have positive work done by the gas. At a lower pressure, at a lower pressure, we have negative work done by the gas, or work done on the gas, positive work done on the gas in this case. So definitely expect to see problems like this on the AP test. There's tons of examples with this in the old AP exam questions, so we'll definitely get some practice on these in class.